My three guests today represent very different segments of the electronic assembly industry. Even though they provide their customers with very different products, my guests are connected through a common reliability concern. One single process failure that affects thermal dissipation of bottom terminated components, intermetallic bond strength, electrical current transmission, and other things, and electrical chemical migration, or ECM. What one single process failure can lead to all of these potential failure mechanisms? Voiding. My three guests today, Tim O'Neill of AIM Solder, who manufactures the solder paste that flows through stencils, like the ones manufactured by my other guest, Prakash Gango of StenTech, and who's left to clean up the residues from all of those processes, Kalyan Nukala from Zestron. I am not doing well on names today, gentlemen. My apologies. A supplier of defluxing chemicals. Now that we've connected the dots between your companies and slaughtered some of your names, let's talk about the science and art of solder paste printing. It's been said that almost all reliability issues in circuit assemblies begin at the solder paste printing process. Most solder paste is applied with stencils. One of the most popular failure mechanisms associated with solder paste printing is voiding. My theory, and we've talked about this before, is that X-ray must cause voiding, because voiding was not really a concern until immediately after X-ray technology made its way into inspection systems. Before we dive down that rabbit hole, Tim O'Neill, explain to those listening what that may not know what we're talking about. What is a solder void and what are the causes?
Thanks, Mike. There are three fundamental types of voiding. The first type occurs on ball grid array packages, or BGAs. When the BGA is reflowed with solder paste, the outgassing products of the solder paste are trapped within the sphere of the BGA interconnect and create what's known as a void. The IPC specification on the largest void that you can have is 30%, and it's 30% cumulative, not an individual void of 30%. It's 30% adding all the voiding together on the BGA. A lot of the X-ray equipment out there today is sophisticated enough to do that calculation for you. The other kind of voiding that we run into is what's called BTC voiding, or bottom terminated component voiding. On a BTC package, you typically have I/O pads on the perimeter of the device. It's a leadless device. There's no solder interconnect like a sphere you'd have on a BGA. It's just solder paste makes the connection between the package and the substrate. And you have a ground pad in the center of this device that often serves as a thermal dissipation mechanism or thermal dissipation feature, so that the heat that's in this package is pulled out of the package and into the substrate, thus keeping the package cool. A void creates a gap in that thermal pad, and that can create a hotspot, because now the thermal energy has to flow around this gap, or this void, and that can compromise the reliability of the package. And then the last kind of void is everything else. As you mentioned earlier, X-ray causes voiding simply because if we were to take a circuit board from an earlier era, pre-BGA, pre-BTC, and X-rayed it, you'd probably find voids in there as well. The simple fact of the matter is solder paste is 50% flux by volume, about 10% by weight, and that material has to go somewhere during the reflow process, and if it gets entrapped in the metal or the molten solder prior to solidification, that's what results in a void.
You talked about 30% being in totality, being the IPC maximum recommended voiding for BGAs. Did that come from any specific research, any specific applications, concerns about heat dissipation, bonding strength, electrical conductivity in specific applications? Or do you think that number was just, educated guess? And is that number, do you think, valid? Are we making too big a deal over voiding? Are we not making a big enough deal over voiding? What's your take on that?
I think the industry settled on 30% for BGA specifically based on the accumulated data that was performed by a variety of organizations, consortia. In particular, Dave Hillman from Rockwell Collins did a lot of work. He's got a great article called The Last Will and Testament of the BGA Void, which I think is probably the single document that distills all the different types of voiding and their effect on reliability most concisely. So if you really want to dig into becoming a void expert, I would start there. The effect on reliability, that's really incumbent upon the manufacturer or the end user to determine if the percentage of voiding, if a 30% void is applicable for the application. Meaning, does it jibe with the reliability profile or reliability requirements of the device? So it is based in science. I think it was a compromise, taking into account the interests of all of the participants on that circuit board, where all the technologies come together: the substrate guy, the component guy, the solder paste guy. So 30% was the compromise. Bottom terminated device, or BTC voiding, the 30% from BGA was adopted for those particular devices. Now, I think there's still data to be gathered as to the effect on reliability. Depending upon who you talk to, you might get different answers. Just as an example, one of the industries that's got a significant concern about voiding is the LED industry, because they're jamming a lot of power into a much smaller space. So they're relying on that solder joint to pull heat out of that package so that it doesn't age more quickly than it should. And in one case, one of my experts told me, he said, "Tim, we deliberately got the voiding up to 70%, and we couldn't measure any difference." So is 30% the magic number? No, but if you have a failure as an end user and you have an X-ray and you X-ray it and you see a high percentage of voiding, you're naturally inclined to presume the voiding has some role in it, whether or not, in fact, it does. So we, as the solder paste manufacturers, simply believe no void is a good void, or less voiding is better. Whether or not that is actually true really doesn't matter when it comes to selling and marketing a product. If it's a high voiding product, good luck.
Right. So we talk about how voiding creates heat dissipation issues, particularly in the case of LEDs. I remember buying, when LED bulbs first came out, I was on this mission to change every bulb in my house to LED back when they were expensive. But my thought was, well, they last 100 years, or they last forever.
Last 100 years.
Well, they don't even, the early ones didn't even last a year. They started flickering, and doing a little light dance on their own. And certainly they've gotten better, but I had to change out all my LED bulbs more than once until the industry kind of caught up with what causes these bulbs to fail. And I know there were some corrosion issues, due to silver material. There were other, heat dissipation issues, but clearly they seem to have gotten their act together in terms of LED bulbs anyway. So Tim, the problem associated most commonly with voiding, heat dissipation and mechanical bonding to the board and current transfer, et cetera. Those are all pretty well documented and understood. But the same issue that causes voiding also causes something that will land in the cleaning world at some point. Connect the dots for me. What's the reason when there is a high amount of voiding, there is also a higher amount of residues under the component? Can you connect those dots for me, Tim?
Yeah, I think so. So on bottom terminated devices specifically, we're not going to include BGA in this part of the discussion. The relationship of the component to the substrate has an impact on void formation. In other words, low standoff devices or no standoff devices practically are prone to voiding. And in fact, one of the techniques we'll probably discuss later with Prakash is how to mitigate voiding with stencil apertures. And the way we do it is with increasing standoff. And so something we've learned is that when you have a very low standoff device, is that flux residue that is trapped underneath that device can have different SIR values than flux residue that has been exposed to the environment during the reflow process. So if you trap flux residue under this low standoff device, the no clean that you're using, I'm presuming it's no clean, may not be as reliable or have the same reliability profile as material that was tested in the traditional IPC B24, B25 test coupon arena. So that's where cleaning may become beneficial in order to reduce the reliability risk on low standoff devices due to entrapped flux.
Yeah, excellent. Now we've connected the dots all the way to your part of the world, Kalyan. As a cleaning material manufacturer, what's your experience in removing residues under bottom terminated components? I know BGAs were the original poster child of hard to get under parts. Now we wish everything had the clearance of a BGA. Tell me about the residue removal from under a bottom terminated component and why that is important to many manufacturers.
Sure. So cleaning underneath the components is challenging always, no matter what type of component we are dealing with, maybe a chip cap or, it could be a BGA or a QFN. I mean, it gets even more challenging when you're talking about BGAs and QFNs in particular, as they have different size as opposed to chip capacitors, and they have the tendency to trap more flux contamination underneath during the reflow process as opposed to any other component type. Take for example chip caps. So that's why cleaning becomes crucial when it comes down to cleaning underneath those type of components. And with the usage of low standoff stencils, mostly 1 mil or 2 mil stencils, it's getting even tougher because you have to have the cleaning process optimized in a way where you're allowing the chemistry to get underneath these components and have enough time for it to clean that contamination during the wash stage. So you have to have the process set up in an optimized way for this to happen, so you're not risking of leaving behind any flux residues underneath after the cleaning process.
The amount of space between the bottom of a bottom terminated component and the top of a board, I mean, it's hard to, you couldn't floss underneath there. It's 1-2 mil standoffs. What are the mechanical and chemical tricks of the trade to get under those components, not just to get under them and solubilize the materials, but to get your material out when that wash process is done? What are some of the tricks of the trade? What are the lowest standoff heights that are really where cleaning is probable, possible and probable? And what are your tricks of the trade when it comes to fully cleaning under these very, very tight bottom terminated components?
Sure. 1 mil standoff has become very common lately. So we have many customers who are using a standoff as low as 1 mil. So from a cleaning standpoint, it's getting even more challenging when you deal with such low standoffs. So when it comes down to a cleaning process, it's always a combination of mechanical energy, chemical energy, and thermal energy. So when we say mechanical energy, we are talking about the equipment in this case. What type of equipment are the customers using? Because you have to match the process to the right equipment. And then is the chemical energy. And then here you talk about the cleaning agent that was chosen for the desired process. And then the thermal energy, in this case, the temperature wise. So all these three has to be in place, optimized in a way that the settings that were chosen should work in cleaning, in getting underneath the components. So mechanical energy helps in getting that chemistry push underneath those bottom terminated components. And chemistry, since it has been formulated to clean these flux residues, at that point will react with the flux, which solubilize the flux residues and then flush them off underneath the components. And then thermal energy actually helps in improving the cleaning, in enhancing the cleaning even better. And all this is again happening during the wash stage. And then it's as critical for the process to rinse these residues off, chemical residues off during the rinsing process. Again, in this case, we are talking about, having an equipment that has a good spray bar configuration. Most of the equipment manufacturers has their own proprietary design. Some use jet impact nozzles, some use V-jet nozzles. Everybody has their unique technology inbuilt into these equipments. So in combination of all these, you can not only achieve best cleaning, but you can also ensure the rinsing to be proper before the board moves out to the drying stage and then comes out completely dry.
Excellent. Thank you. Prakash, let's talk about stencils. Your job is to take Tim's material and push it through very small holes onto the board with the proper alignment and thickness. What are, from a stencil standpoint, what are some of the things that your tricks of the trade bring to reduce or mitigate voiding from a mechanical, from a stencil printing standpoint?
Thanks, Mike. I mean, this is a common issue we hear on a day-to-day from customers, how to eliminate the voids. I mean, from my experience, I mean, there is no way to eliminate them, but we could reduce the amount of void. Like Tim mentioned, I mean, everybody have a standard how much percentage they should have it, how much percentage they should have on a board in terms of void. But as the IPC, there's no clear indication what's the percentage except for BGAs. On the stencil design, the way we could help the customer is helping out with the stencil design. For QFN, DFN type of package, we do certain reductions, and then we apply certain window pane to outgas during the reflow process. For LGA type of package, they're also similar to BGA, but there's no bars underneath. So they also consider as a BTC type of component. So for those type of components, sometimes depends on the package size. We do have step stencils to increase the height that will give you proper outgassing. I mean, it is pretty challenging, but proper reduction and doing proper design, and you could eliminate most of the voiding.
Very good. Are there tricks people are doing with the board design that can lead to an elimination or a reduction, at least, of voiding from masks, creating dams, creating for lack of a better word, for these flux activators and gases to escape?
I mean, I've seen some boards, a lot of boards with beer holes, I guess, to heat to dissipate properly. I'm not sure how much it's effective in terms of burning the flux, but I read some papers with beer holes. Some they like it, some they don't. So it's all over the map. I think we need more studies on this issue, voids. But at the moment, there's no clear indication how we could eliminate completely.
Mm-hmm. Tim, my friend and colleague Eric Camden recently published a paper correlating the, from a no clean flux perspective, correlating the amount of residue based upon nothing more than reflow profile. So they created some test boards and put certain types of components on it, reflowed the board using the recommended reflow temperatures and peak temperatures specifically. They hit a peak temperature of 250 degrees C for whatever time. Then they reflowed identical boards, identical components, identical materials, and cut that peak temperature by 10 degrees and subjected various areas of that board to ion chromatography and determined that the amount of detectable potentially harmful residue was higher when that peak temperature was off by 10 degrees. And I'm wondering if that, even though we're really talking about voiding, there's a similar theme here, which where voiding creates excess amounts of residue. Is that phenomenon of that peak temperature being off ever so slightly, where it might otherwise not cause any solderability issues, resulting in a higher amount of detected residue?
Well, I think you brought up a theme that I think needs to be discussed, and that is how we're all interrelated. Making a change to accommodate one facet of the assembly will often have an adverse outcome on another facet of the assembly. So I'll take Eric's work. I haven't read it yet. I'm going to look it up now for sure. Highly reputable company, understands their business very well. Everything that comes out of Foresight is, very well respected. It's good stuff and good advice. So what I would presume is happening is that due to the increased reflow temperature, you're simply or reducing. I can talk either way. Let's call it increased or decreased, right? So when I increase exposure time, when I increase the amount of thermal energy thrown at an assembly during the reflow process, I'm giving more energy into the system, which increases volatilization, which makes more of the flux residue go up the stack. Conversely, I am exposing the entire assembly to more thermal energy, which can increase oxidation and degrade the flux material more readily. So I may adversely impact wetting performance and thereby increase voiding as a result of trying to make the flux residue more benign. I increase the oxidation levels. I increase the oxidation levels on the component ends, on the solderable surfaces, and they become more difficult to solder over time. And then at the end, when it comes out of the oven and Kalyan has to wash it, he now has a board that will undoubtedly be more difficult to clean, because just like a pot roast pan in the oven, if it's been in there for 4 hours, you got to soak it overnight to get that stuff off because it's been baked on there more. So it's always this give and take in our world. So why Eric was able to measure less ionics was probably because there was less volume and therefore just less material to extract. And it ended up somewhere in the cooling platen in the oven or up the smokestack and not on the board.
Yeah, that makes perfect sense. So Tim, in your world of solder paste materials, soldering materials, what are you guys doing from a materials perspective to mitigate voiding? Are there certain solder pastes that have certain attributes that are good attributes yet create more voiding? Are there solder pastes that create less voiding but maybe come with
how much time do you have?
An attribute,
How much time is this thing going to go on for? I'll talk in very general terms. Okay, none of this is gospel. Everything is, has a million caveats. But generally speaking, no clean SAC 305 based alloys are the most widely used in the industry. That's the yardstick by which we measure voiding. So within that box, I can say a more active paste will typically result in lower voiding. Why that is, I don't necessarily know. A flux that's got a durable activator system that can withstand that high reflow profile, that longer temperature, will typically give you the ability to increase time at temperature, therefore reducing voiding. So those are a couple tools that are in the solder paste guy's toolbox. When you start changing alloys, things change. So one of the things that we've learned in experimenting with the low temperature alloys, which seem to be the buzzy word right now, they don't void very much. They void appreciably less than SAC 305 alloys. Still digging into why that's the case, but That's what we're experiencing. Could be related to flux chemistry because they're not the same flux mediums that we were using with SAC 305. Could be related to the characteristics of the alloy while molten, or what happens to the alloy when it solidifies. Water-soluble SAC-based materials, not anywhere near as commonly used as no cleans, probably have the highest propensity for voiding by nature. They don't contain rosin because they have to be water soluble. As such, the medium, the flux medium, has to do other things with different materials that you try to emulate what rosin does, but it isn't quite the same. So therefore, it lacks some of the survivability in reflow that a rosin-based material might. So we're always, 1/10 of 1% of a chemical in a solder paste can have a surprising effect on something like voiding. So that's what our R&D folks do. They, change a little bit of the chemistry here, run their voiding experiments, observe, see what happens. If it's positive, they keep going in that direction. If it's negative, they take a different direction. It's ongoing, and we're learning more with the more data we collect and the more experience we gather.
Yeah, very good. Prakash, with the proliferation of wearables and e-textiles, as well as the hyper miniaturization of electronic assemblies, do you see a major change in stencil technology? I'm kind of going to ask you all to get out your crystal ball and look into the future. What, Prakash, do you see as technology changes, if any, when it comes to stencil technology moving forward?
I mean, currently we have few processes which very effective when you're doing miniature type of apertures, and there are special coatings that introduced into the market. At StenTech, we have a coating called advanced nano coating, which will increase the transfer efficiency when you are especially printing smaller apertures. Other than that, I mean, right now, I mean, there is no other technology out there, especially, I mean, the lasers got to where it is right now. I mean, they're the best in the industry, and the coating does the magic. And right now, I mean, I don't see any other technologies out there that's gonna evolve anytime soon.
How about solder paste? The machines that dispense solder paste through very fine needles, for lack of a better word, nozzles. Can they handle ultra fine pitch components, or is that going to be the realm of stencils for the foreseeable future?
I'm not too familiar in that. It's called jet printing, right? I'm assuming.
Yeah, yeah, that's one word for it. Yeah.
Yes, I think I've seen few machines out there. They are getting really better, but there are certain limitations how small they could deposit. So it's not still out there, but the only drawback is the process itself is kind of slow compared to screen printing. For example, a board, it might take like few minutes for them to deposit onto a jet printer. On a stencil, it's like few seconds, or like maybe less than 20 seconds, depends on the board size. So it is getting there, but I don't think it's there yet.
Tim, do you see any changes in the future as to the methods that solder paste is applied to boards moving forward?
Prakash is right on. I mean, I don't ever see a jetter keeping up with a screen printer. I see it complementing a screen printer. Mm-hmm. So I've already seen a couple of examples where SPI manufacturers are incorporating jetters into their SPI equipment. So imagine that you're printing the vast majority of your deposits with the traditional stencil, but you have a pin and paste or intrusive reflow area on the board. So you can send the jetter over to augment the volume required for that particular application, or a connector, or something that needs more paste, or a skip plugged aperture, for example, the SPI can detect it, send the jetter over to fix it, so that you get basically 100% yield to the printer. I think that's where the jetting technology represents the greatest value to the industry. I also think there are markets that can benefit from a very highly flexible platform like a jetter, where they're doing low volume, very high mix, doesn't require all the tooling and expense and stencil design resources. You can literally change your deposit profile on the fly. And that market, I think, is certainly a growing market in the U.S. as more development takes place here and high volume production takes place overseas. So I think jetting is going to expand. There are limitations. We really are up against it in solder paste technology in terms of mesh size. Type 6 powder is the minimum requirement for these technologies. As you get down into type 7 and type 8 powders, you're dealing with dust. And these metal powders, in some cases, if you get them fine enough, they just dissolve into the medium. They disappear because there's so much surface area to react with the acids in the flux that it can dissolve the metal away. So that's, I think, the next frontier for solder paste powder development is ultrafine mesh powders. I'll give Kalyan and myself a little plug. We actually co-authored a paper on cleaning those residues from jetting products because they use such fine mesh materials. And it's a perfect segue for him to pick up the topic. And you don't even have to do your job.
You need the host anyway. Kalyan, I'm going to have you pick up on that, but I just want to say one thing. When I kind of look at the jet printing in a very similar context as 3D printing, you can do wonderful things in low volumes and not very quickly. But they certainly
agree. It's very analogous.
Yeah. So Kalyan, as a cleaning equipment manufacturer myself, I can confirm the return of cleaning as a process norm. We witnessed the cleaning process go from conventional wisdom back in the, before the 90s, basically. We went from a conventional wisdom status to kind of an outlier status where just super high rel people were cleaning, and pretty much all of class 1 and 2 abandoned cleaning back in the Montreal Protocol days when the solvents were banned. Where do you see the future of cleaning going? Is cleaning here to stay again, or do you think it's a process fad? Now, I know you don't want to see it as a process fad because that's your industry and my industry as well. But it was here. It did go away for the most part, and now it is back again. Do you think we'll overcome the obstacles that are making cleaning required again, or do you think the drive and technology and the specific designs that the modern technology brings will guarantee cleaning for at least the foreseeable future?
Yeah, frankly speaking, Mike, I don't think cleaning will go away, because even now, if you look at majority of the industry, even though many stick with no clean process and don't clean, you still have the same percentage of people who still prefer cleaning even if they're using no clean. And with the latest challenges in the board design and like the miniaturization becoming more common now, it's going to get even complicated. So a customer, even though he is using no clean, I'm sure at some point it will make him think like, how effective is this no clean? So at least it will raise a thought in his mind that, maybe I should consider cleaning at some point. Because, he may have one customer who is okay with not cleaning the boards, but the others might come back and say, hey, you know what? From what we have been reading, from what we have been hearing, we think, cleaning the boards would be a better option than just leaving them, unclean for we don't know how long. Because, unclean boards, on an unclean board, you don't see a failure right away. It might take some time for that to show up. So, but once it shows up, it's been considered a failure. So I think people at some point, will definitely, think twice about, getting away from cleaning completely. So I think cleaning will definitely stay. Over the course of time, with the new challenges that are already there, and I'm sure some new technology will come into picture a couple of years down the road. So it will keep us occupied. It will make us think twice, and I'm sure even customers will also start to think, how critical is cleaning to the life cycle, to the product life of the boards that they're building.
Excellent. So I'm going to put you guys on the spot. We didn't go over this question previously, but I think you're all very capable of answering it from your unique industry perspectives. So IoT, Internet of Things, which I've railed on this show for a long time, which is basically the process of putting electronics in things that don't need electronics in them and then throwing them outside, and connected toothbrushes and things like that. I think IoT, and particularly IIoT, has some really good value to it. But we are putting electronics into consumer things that really aren't class 3 devices. They're arguably class 1, maybe class 2, but probably a lot of class 1. So what are the challenges that each of your companies face? We'll start with Tim. As electronics move forward, as reliability expectations get higher, as component densities get higher, as standoff heights get lower, as the expected life of a product becomes longer, we're all and the cost people are willing to pay for it goes down. This is the perfect storm of an explosion in technology and no one really willing to pay for it. So what Tim, we'll start with you. What do you see as the challenges our industry will face when it comes to reliability, whether it's voiding or other maybe yet to be discovered or yet to be appreciated failure mechanisms? What do we have to overcome?
I can only speak for my industry, right? I can't speak for everybody's industry, but it isn't just IoT. I think it's ADAS for cars and things like that. Reliability, I would say it's reliability first and foremost, not necessarily for longevity, but for consistency. It's got to work every time it's supposed to work. I don't know that it needs to last 20 years, but in the lifespan that's anticipated for it, it's got to work, especially if it's driving your steering wheel. So that means that the alloys have to be able to withstand a greater number of heat cycles, for example. Particularly in the automotive arena, things are getting hotter, longer. As you said, they're finding their ways into applications where they don't really belong, but they're expected to work. A byproduct of all this miniaturization is heat. And so things are going to be getting hotter and colder, with a lot hotter and a lot colder with a lot more frequency. So I think alloy development is at the fore of certainly our efforts, as well as increased electrochemical reliability from the solder paste residues. We need high SIR values, robust materials as it relates to soldering, which are in conflict. So those are the challenges that we're addressing with the upcoming materials specific to IoT and ADAS and things like that.
Yeah, excellent. Yeah, automotive is a big one. Most people don't realize outside of our industry that unlike a traditional car, the electric automobile, the fully electric automobile, turns on when it ships from the factory, and it doesn't turn off until it's crushed in the crusher. It's on all the time to some degree, and I've said this on this program before. The reliability associated with electronics in cars has gone from infotainment and widgets and seat massagers and automatic door locks and key fobs to LiDAR, spaced distancing for adaptive cruise control, to blind spot monitoring, to electronic steering and throttles and
brakes.
Things. We have become worse drivers because I don't look over my shoulder anymore when I change lanes because I trust my blind spot indicator. And so these, unlike the aviation industry that has a high degree of automation and at least 2 redundant backup systems in case the first or second one fails, automobiles basically have one board, one computer for one process, and that's it. So there's no backup. So they do have to work. And I think we are all becoming worse drivers because we're relying on this absolutely marvelous technology. And now the technology cannot fail, because a failure in an automobile circuit board will no longer just mean your antenna will not go up by itself, or you won't be able to get Sirius XM radio. Now it means your car may not stop when it's supposed to, or may not warn you of a hazard when it's supposed to. So yeah, I totally agree. Prakash, from your part of the world, what things keep you up at night? What do you think some of the challenges are when it comes to printing, stencil design specifically, as we move forward in this amazing age of electronic evolution?
Thanks, Mike. Right now, I believe the smallest component that we are printing is 105s, and there are other components which are even smaller than that. But majority of the customers, they try to keep it within 105s and up. And we have the technology. We are ready. I mean, we have special coating, like I mentioned earlier, that will do miracle on these smaller apertures. But it is getting challenging if it's gonna go beyond that size. I mean, anything below 0.05, 105s, and anything with smaller pitch. But as so far, like, I mean, we are good. I mean, we are ready for the challenge, and I think our technology supports most of the miniature components out there in the market.
Yeah, it's amazing to me. When I give my workshops and things like that, I have a slide that I've been showing for years. It's completely obsolete. It's a small surface mount component. It's probably ½ inch square. It's about this big, and like gold wing device or something. And I would show that, and I tell my audience that my civilian friends who are not in this business will look at that slide and marvel, like, how in the world can something get so small, and how can you put so much technology into such a small package? And then I say, well, that's actually 10 years ago. And then I show a component on someone's fingernail. That's what we're dealing with today. I have no idea how pick and place machines can even see these parts and place them with any degree of accuracy or polarity. I have no idea how you're able to cut a hole so small in a stencil and push solder paste through that hole with any degree of definition and accuracy. That boggles my mind, but clearly you guys managed to do that. Kalyan, what besides Tim finally coming up with a flux that never under any circumstances needs to be cleaned, and also cleans up whatever residues were on the board before the flux went on, besides that improbable development, what keeps you up at night? What are some of the challenges facing the cleaning industry today, and where do you think those challenges are going to go? They're going to get worse? They're going to get easier? What's your prediction?
Cleaning challenges, Mike, that we deal day to day, they're countless. What we deal with today, we don't deal with it tomorrow. But the good thing is, once we learn how to resolve that issue, at least it's a knowledge that you have gained. So if things like that show up at different customers, you can just step up right away and then offer them recommendations. But like I said, these challenges are countless. New technology comes in, maybe not now, but 6 months down the road. So you're dealing with new challenges at that point. So what all challenges that you have dealt with so far, I won't say they become obsolete, but it's just a knowledge that you can keep it within yourself. But you should be ready, proactive to face the newest challenges that you'll be encountering in the coming years. And with the miniaturization, and then with the technologies like you mentioned, IoT, and then electric cars, and then 5G, I'm sure even before 5G becomes common for everybody in this world, I'm sure they'll start working on the next generation. So even before you get to know fully about the challenges of 5G, you should be even thinking about, okay, what challenges will we be facing with the next technology? It's an ever-evolving world. I mean, you can never say that you've known everything to face this world. I mean, you might have a good sleep today, but next day you might wake up with a totally new question, new challenge, and you'll be again back to square one, scratching your head, opening up the books, reading up, getting to know more about the technology so you can even understand it better. so you can further assist or the customers on how to get that resolved. So in my opinion, I mean, the cleaning challenges will just even get better and better, in a sense that they become more challenging from time to time, and we just have to just get used to it. And then the more we learn, obviously the good for all of us too. It's good to share our experiences with everyone, like what we are doing now, and also with customers, so we learn new from the customers what they have encountered. So it's like give and take situation. You learn something new, you share it with somebody who doesn't know, and then in the same way you learn something from the others, the issue that you have not encountered in the past. So it's a cyclic process. It just goes on and on. I think this will just keep going.
Well, that means all of us can get up tomorrow with work to do. That's what it sounds like.
Yeah, exactly. I mean, yeah.
Okay, so before we say goodbye, I'd like to do a little roundtable wrap up for a few moments. Tim, do you have any parting thoughts for our audience?
Wash your hands, wear your mask, and buy AIM.
Wash your hands, wear a mask, and buy AIM solder products. I like that. I think maybe 3 out of 3, certainly 2 out of 3, but maybe if you're lucky, Tim, 3 out of 3.
It's all good advice. It's all good advice.
It is good advice. I always end my podcast I do with, or actually a tips and tricks video series that I do with, stay well, stay healthy, stay happy. That's the part I think a lot of us are forgetting. Stay happy.
Yeah.
Kalyan, any parting thoughts for our audience?
I was going to talk about COVID, just stay safe, just be careful with everything that's going out there. I guess, the health matters most than anything else now. So just stay safe, follow the protocols, and hopefully we'll get through this, and then few months, everything will be back to normal, and we'll be glad we survived.
Yeah, particularly these days, as everything seems to be raging at the moment, kind of the wrong kind of rage that we want.
Yeah. So
Both kinds.
Right. Prakash, any final thoughts?
In terms of voiding, I mean, it's always design. You have a good design in place on your stencil. I mean, you could reduce the amount of voiding, and choose the correct paste. That'll go a long way, and clean your boards. And I hope everybody stays safe, and we could get rid of this COVID.
Yeah, I'm sure we're all very anxious to put this behind us. So everyone working from home, or are you in the factories?
No, we're working from office.
Office, yes.
Yeah.
Home.
And Tim, is that normal? Do you normally work from home, or are you normally in the office?
Normally in the office.
Okay, so it is a difference for you. Yeah. Well, thank you, gentlemen. For those of you who would like to ask our panel additional questions, if you go to our main Reliability Matters site at Spreaker.com, Spreaker.com, that'll be down on the screen somewhere down here. You can see the show notes, and within the show notes, I will have the contact information, email addresses of our panel. And they've already willingly invited me to let you know how to contact them. So if you have any questions about voiding or cleaning or stencil printing or anything else that falls into their purview, don't hesitate to reach out to them. I know that they are eager to reach back out to you and provide you with the answers that you seek. Thank you very much, panel. I really appreciate you all being here today and the expertise that you impart on a regular basis, but particularly on this show. Thank you all very much for being part of Reliability Matters.
Thank you, Mike.
Thank you for having us.
Thank you, Tim. Thank you, Prakash.
Thanks, everyone.
Yeah.
Thank you.
Okay, with that, stay safe, stay healthy, stay happy, and we'll see you again very soon.
Yeah.
Well, that's another episode. Thanks for listening to the Reliability Matters podcast. Don't miss an episode. Subscribe to Reliability Matters on iTunes, Spotify, iHeartRadio, or wherever you get your podcast. Reliability Matters and other reliability-based podcasts are available at Circuit Assembly's PCB Chat at pcbchat.com and at Ascendo Reliability at reliability.fm. Thanks for your comments. Please keep them coming. Send comments and episode suggestions to mike@mikekonrad.com. That's Conrad with a K. Until next time, thanks for listening and keep doing it right.
Thanks for listening to the Reliability Matters podcast. Join us on the second and fourth Tuesday of each month for new episodes of Reliability Matters.